Okay. So we were basically revising a couple of network theorems that we already know with the backdrop of relating it to what a voltage source or a current source should look like. So we had also looked into the proof of substitution theorem, Thevenin's theorem. I didn't go into the proof of Norton's theorem because, I mean, I presume we'll be able to do it because it's basically the same thing. Instead of replacing the output load with a, just like we, in case of Thevenin's theorem, we replace the output load with a current source and did superposition and all. If you do the same thing by replacing the current source with a voltage source and you do superposition, you will end up with the expression of Norton's theorem. I will encourage you to do it yourself, just to convince yourself that you can come to Norton's theorem with using the same principles, right? So what I would like to do next is to spend maybe 5-10 minutes on source transformation, because that is again something that will be very useful, and then we'll move ahead with the crux of the course. So let's assume that we have a voltage source, some source resistance Rs, connected to some network. Okay, so this network, there is no constraint on the network per se. I mean, this network can be nonlinear also. So what I would like to do is to, so this is V in. What I would like to do is to see if I can replace this V in with a current source. This contraption of V in and Rs with a current source, with the hope that this network N won't get to know, right? This network N won't understand that any change has happened. So if I can do that, then essentially what I am trying to ensure is the voltage across this port, let's say V1, and the current that is going into this port, let's say I1, if we can ensure that the voltage V1 and the current I1 remain constant or remain unchanged, regardless of what I do to the current to V in or Rs, then the network won't be able to understand that anything has changed anywhere anywhere else in the circuit. Do you agree with that? Okay. So in order to do this, then naturally I cannot do anything on this side. I should be doing everything on this side, right? Because network N is not in our control. That is something that we should keep unchanged. Okay. So if that is the case, what we'll observe is, what is this current? Let me redraw. So this voltage is V1. So this current is V in minus V1 over Rs, right? So since we would like to replace this V in with a current source, then it probably makes sense to express everything in terms of some current minus some current, right? This, instead of writing V in minus V1 over Rs, what I would do, I will write it as V in by Rs minus V1 over Rs. So note that V in and Rs both are properties of the source, right? So I can as well say that if I can get another source which has, so this is this V in over Rs minus V1 over Rs is, pictorially, it should look something like this. If I have a current source of value V in over Rs, and I take out some current V1 over Rs, and maybe something is connected here. What is the current that is going in? Right, same, right? So V in over Rs minus V1 over Rs. So do you think this situation and this situation is same as with regards to whatever is happening to the network N? Yes, right? Because ultimately we essentially did nothing but to replace. Essentially, it's like saying that we are using substitution theorem again, right? So this current I am keeping constant. The current that is going into the network is keeping constant. And the voltage V1 will also be the same because we derive the current from that voltage V1, right? So the network N will not know that anything has changed. So are you with me with this? Do you agree? Do you have any questions? Okay. So now one key observation. Do you think this source V in over Rs is a independent source or a dependent source? Dependent on what? Independent, right? Independent source. Great. What about this guy? That is a dependent source, right? So I'll have to, dependent source, we have a different symbol. So it's a dependent. What type of dependent source? So we know, I assume all of you know there are 4 types of dependent sources, right? Voltage controlled voltage source, voltage controlled current source, current controlled voltage source, and current controlled current source. Are you aware of this? Yes, sir. Okay. So what type of dependent source is that V1 over Rs? Great. So it's a voltage controlled current source. Thank you. So what is the control voltage here? So the voltage control current sources are typically, these are two input terminal, 2 output terminal devices, right? Or symbols. So what should I do with the, basically I'm asking what should I connect to the 2 leads that are coming out of the current sources, of the control source, right? So what should I do with the bottom lead? Okay, so ground. So let's say we have to take one reference. Let's say I take this as a reference and connect it here. What should I do with the other one? It should be V1, right? And which terminal? Do you have any terminal which is V1? The top one, right? So, so the top terminal is V1. So essentially, if I connect, so let me redraw it in a slightly different way. So, this. So essentially, if I connect, if I take this, if I take a voltage control current source and connect one of the terminals, so let's say I call this G times V1 minus V2, and this is V1, this is V2. If the one that is that has the negative sign attached to it goes and connects the way I have shown, and the other one goes like this, then essentially we end up with the same structure. But do you think this is a special type of control source in the sense that, yeah, it's a control source, I understand, but can I replace the control source with something? Any element? A resistance. Why? Right, exactly. Great. Thank you. So if I look at the black box, if I just look, if I don't know anything and I look through the terminals, what will I observe? I'll observe that the voltage across this terminal is V1 and the current through this terminal is V1 over Rs. So this is nothing but not a resistor, right? So what essentially we did was, by doing this, we turned a control source into a resistance, right? So this is quite obvious, but in another sense, this is quite profound also, because as you can see that it's not as if you can take any control source and turn it into a resistance. It's not as if you can just take a voltage control current source, connect it anyways, and it will become a resistance, right? So it became a resistance because we were able to establish a relationship between the current and the voltages across the same ports, right? In a voltage control current source, the relationship between the output current and the voltages are not with the same port. In general, the port current is dependent on a voltage which is connected somewhere else. If we can make the dependency with respect to the same port, then essentially it becomes a resistance, right? Okay. So now, which essentially means that I can now replace our same stuff with a input current source whose value is V in over Rs. This, whatever was Rs earlier in series with a voltage source, became an Rs with parallel to the current source, and this becomes a network. Okay. So, so one might say that, no, so before I move ahead of myself, so where did we start? Where did we start with? We started off with saying, if we can replace this circuit in such a way that this V in is not a voltage source anymore, it's a current source. And as you see that following the logic or arguments that we made, indeed we can do. So this is another way of one of you, I heard somebody said that it's similar to Norton's theorem. Yes, in some ways it is similar to Norton's theorem, but in some ways it's not. Because in Norton's theorem, what we essentially do is look into the network N and try to replace it with its equivalent open circuit voltage or short circuit current and output resistance, right? So this way you can prove Norton's theorem in another way, but this is not Norton's theorem. Okay, so this is a source transformation. We did a source transformation. We were able to transform the series combination of a voltage source and its resistance with a parallel combination of another current source and the resistance. And in both cases, the voltage source and the current source are independent sources. Another critical point is this source transformation is valid even though if this network N is nonlinear, because we didn't do anything to the network N, and only theorem that we established was substitution theorem, or used was substitution theorem, right? It just when we replace the sources, right? When we went from this step to this step, we essentially said that the port voltages and the currents don't change, so I can kind of use substitution. Okay. Okay. So so this is as far as revision of the basic network theory or the basic network theorems are concerned. So now let us move on to the crux of the course. Okay. Any questions before I move on? Yes. Yes, it's a proof. You can say that I haven't taken one extra step. If you just take one extra step, you'll be able to prove Norton's, right? But because basically what you are saying is any network, any linear network, I can replace with a voltage source and a resistance in series, then take this step, you'll be able to prove Norton's, right? So that is one step from this, but this is not Norton's theorem. So the reason I am harping on this is when you are using Thevenin's theorem, you are essentially trying to look into a linear network and linearize it, right? But this theorem is not that. Whatever we proved, I showed you just now, does not depend on the network N. It can be nonlinear also. We are only doing something with the source and saying that the sources, if it is not a part of an internal network, regardless now the internal network can be nonlinear also. I should be able to replace the voltage source and the current source, the voltage source and resistance with a parallel combination of current source and the resistance. That's all it is saying. Even though it looks very similar, but it's not the same with respect to Norton's theorem. Yeah. Right. In Norton's theorem and Thevenin's theorem, we are trying to look into the network, whatever the network is, and trying to model the network. In this case, we are not looking into the network. We are saying the network is present. Everything other than the network is linear. Then can we do something about it? Okay. This is another way to, I mean, you take another step, you will be able to prove Norton's. It's pretty simple, but this is not Norton's. Okay. So we have been dealing with, question? Okay. We have been dealing with linear circuit elements or LTI circuit elements to be more specific till now. But as I had alluded to a couple of classes back, that most of the actual real life electrical networks, electrical elements that you will see are nonlinear. Even the resistors that you find out in your labs, under certain conditions, they are also nonlinear. Right? I mean, that might not seem very intuitive. And an example that I can give you is, let's say you pass a lot of current through a resistor. Let's say you pass a sinusoidal current through a resistor. Okay. In sinusoidal, when say this is the current profile through a resistor, and you can assume that this current is huge. It's a very high value of current. So when you pass current through the resistor dissipates power, heats up, right? It heats up. So if you now plot the heating profile of the resistor, what will you observe with respect to time? It will be hot when the current is high. It will be not so hot when the current is close to zero, right? So it might not be observable, but the mechanism is happening inside. Okay, so now depending upon what type of resistor it is, it might heat up or cool up very fast, right? And depending upon what type of ambient conditions that you have kept for the network. Now, if that is the case, if a resistance heats up, you know what happens to the value of the resistance? Any idea? It increases, right? Because resistance is essentially, it's resisting the flow of charges, and the existence of resistance comes because of thermal fluctuations inside the material that essentially is making the resistance up. So in other words, what I can say is that with the temperature, the resistance will change, and now temperature is dependent on the current that I am feeding, which means the resistance will change with the current. So resistance is no longer constant with respect to time, and that is a classic case of a nonlinear system, a nonlinear element. The reason we are not going to deal with any of these type of things in this course, but the reason I wanted to give this example was to give you the feel that in principle, nothing, I am categorical that nothing that you use in your labs are perfectly linear, right? They are linear approximations of some nonlinear phenomena. So now if you have to deal with actual nonlinear elements, then you have to develop a framework as to what to, just like we have a framework of dealing with linear elements, right? So we have done multiple courses of linear analysis, right? So we should also have some framework of dealing with nonlinear elements, because ultimately, the bedrock of dealing with linear elements is superposition. We start off assuming the superposition holds, then we go ahead and prove multiple theorems. But we don't have such luxury while dealing with nonlinear elements. So as we tend to do, we human beings tend to do, in almost all situations, which is we are not particularly familiar with, we try to model it with another situation that we are familiar with, right? And then try to solve that familiar situation and go back. That's what we do every time in real life also, right? The moment we find out something, it's like that example of, I don't know whether you guys have heard, when we were kids, we used to hear the story of a student who went to had an English exam or something, and he knew that some essay will come, and he essentially marked up some essay on a river. But when he went, he said that saw that some essay on a dog has come. What is good to say? He thought for some time and said that there was a dog. He was very thirsty. He went to the river, and basically the river was this, river was that, and he wrote whatever he wrote. So this is basically something similar. We all engineers tend to do, right? So we have something. The moment you are faced with something unknown, you try to see if I can model that unknown with something known, because then I know many things about the known stuff naturally. So if I can then do something about it, I go back to the unknown after that, right? So in some sense, we all tend to do that. So that's what you will see we will be doing in the next two lectures also. But what is that step to go from this unknown to known? That is a critical step, and that's what we'll be focused on. We'll focus on in today's class and part of the next class. Okay, so let's start off with a very basic nonlinear network. So let's say I have a voltage source, V in, resistance R, and a diode. Are you familiar with the current equation of the diode? Okay, great. So let's say I have a diode. We won't get into how the equation came into being. That is a part for a device course, more specifically E311. When those of you will take it, will get to know. So this ID is IS e to the power. Can you help me? If this is VD is the voltage across the diode, VD over V thermal voltage minus 1, where the thermal voltage is KT over Q, which is approximately 26 millivolt at room, right? So again, we take approximations. I mean, 26 is a very unwieldy number to do exams mathematics with. We'll say it's approximately 25. If you don't believe me, I suggest just change the temperature slightly, right? So that's what we'll do for the rest of the course. We'll assume that this is approximately 25. Okay, so now before I proceed with this, so what does the current voltage characteristics of if basically what happens if I plot this ID with respect to VD? So it should look something like it's an exponential. It's an exponential at least when VD is more than the thermal voltage. So if I say that thermal voltage is somewhere here, so it should look something like, I mean, in a log scale, it should look like a straight line, but in a linear scale, it should look something like this. And as I go negative VD, at very large negative VD or VD much greater than mod of VD much greater than thermal voltage, it should look like what should it look like? ID? IS, negative IS, which means it should look like this, right? So something like this is going to happen. So have you heard of this thing that the open circuit, I mean, the voltage across a diode is equal to 650 millivolt or 700 millivolt? We approximate it as, right? So where do you think that approximation comes from? Because here it looks like as long as the diode is on, the voltage can also keep on changing, right? Because this is the equation. This is not an approximation. This is the equation. So I mean, any idea why do we take that 600 millivolt or 700 millivolt or 650 millivolt, whatever that number may be, and we sometimes assume that if the diode is on, you replace the diode with that number, the voltage source of that value. We all have done circuit theory solutions with these, right? I presume you have done. Yeah. So any idea why we do that? Because from here it doesn't look like. Correct. Perfect.
We can approximate that with change in voltage, with change in current voltage is constant.
Right. Agreed. Then go ahead.
That's why we can approximate that some current is flowing.
Right. Exactly. So what his point is exactly right. That looks like for a small change in VD, there is a lot of change in current. So I can say that if the current has not changed much, right, then the voltage hasn't changed approximately at all, right? But now the question comes, why this 600, why this 650, why 700? Because it looks like VD is continuous, right? I can be somewhere here, then value of VD will be something. If I can be somewhere here, value of VD will be something else. I mean, they seem to be quite far apart, at least in the plot, right? So the reason behind that is there is an unknown there is a statement that we don't make while we replace that diode with a voltage source. The inherent assumption is that we are operating under some known range of current. So inherent assumption is that if we are operating somewhere here in this region, I know that current maybe changes only in this range. Then probably I can say that the voltage I can approximate with this value. But if the range of current that I'm interested in is probably somewhere here, then the value that I'll be replacing the diode with probably be somewhat here. So the range matters. And also the type of diode, I mean, the material with which you have made the diode also matters. If it's a silicon diode, it will have some voltage based on some current range. If it's a germanium diode, it will have some other voltage based on some current range. So generally, what we tend to see is that if you use silicon diodes in the ranges of milliamps of current, right? Let's say milliamp to 10 milliamp in that range of current, then you get to see a range of voltage. And that range of voltage is quite similar to 650 millivolt or 700. I don't remember whether it's for germanium or silicon. Well, let's say for silicon, let's say it's 700. So in the range of, let's say, milliamps of current, the observed voltage is of the order of 700 millivolts. But if I change the range and I say I am interested in 1 to 10 microamps of current, then clearly the range, that voltage at which your on voltage of the diode will be pinned is not anymore 700. It probably will be 610, 630 or something like that. Now, if I'm interested in 1 amp current, then that voltage with which you are replacing that voltage source with which you are replacing a diode will no longer be 700. It will probably be 800 or 850. So the range matters. Okay, so the reason again I am harping on this is because what you are approximating your element with, we've approximated the diode with a voltage source. What you are approximating the voltage with is highly dependent on the range of approximations that you are making. So the knowledge of the range of approximation is important. Okay, so not particularly necessarily for this type of problems, it's kind of for all problems. Right? This course we'll make tons of approximations. And the knowledge about under what circumstances those approximations are valid is extremely wide. Okay, fine. So now let's say we are interested in we are interested in this voltage value of V out, the voltage across the diode. This is V out. So how should I go about solving this? And let's assume that we cannot replace the voltage V out with a current source or with a voltage source right away. I mean, of 700 millivolt or something. We'll eventually do that at some point. But if I start off with this, how should I go about solving this? Use KVL, right? You can use either KVL or it's a single loop. You can either use KVL, KCL, it doesn't matter. But essentially to solve any network, you require three things. You have to apply KVL, KCL, and you also need the current voltage relationship of all elements in the network, right? All three things put together, you will be getting set of equations to solve the equations, right? So that's what we will be doing. So let's solve. So let's assume that this current is I. So let me call this I1. So V in is equal to I1R plus V out. Now, V out is basically the voltage across the diode. And when the diode is on, right, one approximation that we can readily make as long as V out is more than VT is that the current I1 is approximately equal to IS e power VD over VT. We neglect the -1 because, again, obviously ease of life. Because what I'll do, I'll take out VD here, and then this becomes VT ln of I1 by IS. So I'll replace, in this case, my VD is V out, so I should use V out. So I'll replace this V out in the from the equation on the top with whatever we found. So this becomes V in is equal to I1R Pt Y1 by Is, right? So this is a terribly nonlinear equation, and obviously you cannot solve it using all the um, analytical methods that we know. This is a transcendental equation, and you have to use whatever favorite network nonlinear equation solving tools that you have. You have done this Newton-Raphson method, this type of. Have you done or no? Solving nonlinear equations numerically. Yeah, right. So fine, it's trapezoidal, Newton, whatever. So essentially, if we have to solve this, you have to use any of one of those tools. But I promised you that we will, in this course, we will not get into this type of business. So we will be finding out ways of not solving nonlinear equations, right? So what we'll say is that if we have to solve it in some way, we will either assume that somebody else has done the job for us, or we'll put it in some simulator, and the simulator will tell us what's it going to be. Okay, so that is something that we are going to assume. So, but we all agree that solving this equation is a non-trivial task, right? You'll have to spend considerable amount of time and effort to solve it, and this given the fact that there is only one nonlinear element, and there can be tens of diodes and transistors and all those things. Then what do we do? So it's not as if we were particularly interested in solving only this equation. We are interested in developing a framework as to how to deal with nonlinear equations when we have many nonlinearities, right? So the assumption behind, again, is that we are able to solve this given that we have a simulator or some nonlinear equation solving tool. But when you are designing, you cannot go back every time to figure out whether I do some change, I put it there, and then try to figure out whether things are going to work or not. So that will not give you any, that will not give us any insight as to how to change the network if I have to tweak something. For example, in case of a resistor, if you have a resistor and you put a voltage source across it, you know the current through it, and I want to increase the current, I know either have to increase the value of the voltage source or have to reduce the value of the current, reduce the value of the resistance. Very trivial example. But when you have a bunch of nonlinear elements, I want to have that same type of intuition as to what should I do to those nonlinear elements or something else in the network in order to reduce or increase the current, right? So that's why it's not about calculation or solution of that particular network. It's about developing that intuition as to what should I do. So for that, we have to find other ways, right? So, but given that we need to use some sort of numerical approximation, we'll resort to those things as and when the time comes. So let's say we have done this, we have put this in a numerical simulator, or you have used your favorite nonlinear equation solving methods, and you have found out a solution. You have found out a solution, and you come to me and say that is, so for this, let's say if this is 1 volt, or this, and let's say R equal to, I don't know, maybe 10K, you found that this voltage is maybe 640 millivolt. Nothing holy about 640, but just picked a number. I said, great. Now what I am doing, I'll say I'll change this 1 volt from 1 volt to 1 volt plus 10 millivolt. Tell me the answer. What are you going to do? You are again going to go back to the simulator or go back to your numerical solver and do this entire thing again, right? So that obviously will give you the answer, but that's not what we are after, because what we are after is to figure out if I change things slightly, if I perturb any network, or if I perturb any set of equations slightly, can I figure out a way, a more intuitive way to understand what is happening to the change? Right? That's the whole goal of when I say that if I change it slightly, what is going to happen? So essentially what I'm saying is, if I'm going to change this, so this V in, let's say I change V in from V in to V in plus delta V in, let's say. So I will have a different current. I'll have I2R plus Vt ln of I2 over Is. But what I'm interested in is, can you give me a quick approximation of how much this I2 will be, given that I already know I1. So there is a saying in the industry that in your manager will probably want a very approximate answer today than an accurate answer 1 week from now. Right? So because a quick and approximate answer helps in decision making. So same thing with design. We would like to have a quick answer in next 1 minute, rather than sit and think about what the answer will be if I solve the entire thing to the nth decimal point and take 1 hour, right? So that's what the motivation is. So now, moment I say I perturb, something should ring in your mind that have you done this perturbation equation solving anywhere? No? Okay, fine. Doesn't matter. So essentially what I'm saying is, I know that if I perturb or change the voltage somewhere in the source, in this case, then obviously the current is going to change, right? What we're after is that how much the current changes. Right. Why do you say that?
Because if we subtract this and it is coming out to be I2 by I1, so I approximated that.
Correct, exactly, right? So what he essentially said is that already 1 step ahead of me. You subtract these 2 equations, you get something cancels and something remains. Whatever remains seems to be only a function of delta V, right? So that's what we are going to do, right? That's exactly what you are going to do with, again, not necessarily for this particular network, but for assuming it's any type of nonlinearity, right? So, let me take that step then. So what we are essentially then going to do is to say that, forget about the diode. Let's say we have this arbitrary nonlinearity whose I is something f of b, right? So this is I of E this IE is some nonlinear function of the voltage across it. Diode is a special case. So we do the same thing, and let's say we had this input V in, this R, let's say this is V out. So this current I, or let's say I1, or rather, if I we wrote the KVL in the previous case, let's write the KVL here also. V in is equal to I1R plus f of V out. Okay. So then we say that I have changed the rules of the game. I said that V in I don't want. I want V in plus delta V. Tell me the new output. So you write out the same KVL. V in plus delta V will be this I1 has now changed, right? So I1 has changed to I2. Instead of I2, what I'll say is that it changed from I1 to I1 plus delta I. And I'm not saying that delta is linear. Delta is the increment. Okay. And this becomes, sorry, this is the function of I, right? So I wrote it in a different way. So let's assume if I have to draw the analogy with a diode. So let's say this is the voltage is a function of current. That's just like we did in this case, right? We wrote the voltage in function in the inverse function, right? So let me reframe this. Let's say VE is some function f of I. So this becomes f of I1 plus delta I, right? Okay. So now, as he suggested, if I am interested in delta V's and delta I's only, then it looks like I subtract the top equation from the bottom. I'm left with. So if I subtract these two, so 2 minus 1, if I do, then I'm left with delta V is equal to delta I times R plus f of I1 plus delta I minus f of I1, right? So now this should already ring a bell, that where we are going with this. So we can approach this from two perspectives. Let me use the most relevant one under these conditions. I assume all of you know Taylor series, right? So what is how is Taylor series helpful in this case? Right. Great, right? Exactly, right? Great. So we can essentially say that. So before I go into the Taylor series equations and all, what is the philosophy behind Taylor series? The philosophy behind Taylor series is, let's say I have any nonlinear curve. Let's say this is V and I. I mean, forget about V and I. Let's say this is some cyclist, speed of a cyclist, velocity of a cyclist with respect to time, right? It keeps on changing at different points of time. And let's say I want to, and I want to cross the road, and I'm seeing that the cyclist is approaching me. I know this curve. I mean, I know this, probably my friend or somebody. I know this will be the more or less the kind of VT characteristics that he or she will follow. So maybe I know already I'm sitting somewhere here. At this point of time, I am trying to figure out where the friend will go in the next time instant. What do I need to know? I need to know the current location and I need to know the velocity. Right? If I know the current location and the velocity, I should be able to extrapolate where the next position will be. But if the velocity changes, accelerates, I need to know the acceleration also. That is a double derivative I need to know. If the acceleration also changes, then I need to know the triple derivative and so on. Now, depending upon how crazy my friend is, whether this goes like this or it goes like this, I need to know more and more number of derivatives. If the prediction is pretty steady, that is, it's completely straight line, then I only need to know the first derivative. If not, I need to know multiple derivatives, right? So that's what Taylor series essentially telling us, right? So what is Taylor series telling us in this context? In the context of the circuits, if I1 plus delta I is equal to the current value of current before I applied the extra voltage, or in this case, I'm trying to figure out the delta I. The current value of current f of I1 plus some extra stuff. What is that extra stuff dependent on? The extra stuff is dependent on the delta I that I have applied, or in this case, I'm trying to observe, and the slope, right? So it will be delta I times f dash A1 plus delta I squared by 2 and so on. Correct? So now when we now say that I'm interested in only small changes, right? I'm interested in small changes. What am I saying? I'm essentially saying that we probably will be, we are only interested in those values of those ranges of changes where all these higher order terms are negligible. Okay. This is that step that we are talking about, that we already know how to solve linear equations. I need to figure out a framework to solve nonlinear equation. This is the critical step, right? Neglecting the higher order term, right? Where you cannot neglect the higher order term anytime, that you just, because it solves our purposes. You have to be diligent and you have to figure out that you have to develop a condition, or you have to develop a circuit condition under which those higher order terms can be neglected. Okay. So if we neglect this, so as long as we can neglect this, so what's going to happen if I subtract? Now, basically, I am left with this f I1 plus delta I minus f I1. So your delta V becomes delta I R plus delta I f dash I1 plus bunch of nonlinear terms. Correct? Agreed? Okay. So again, till now, no approximation. Till now, everything is valid. But if we make an approximation, right now, this is the critical approximation step. Under the condition that if nonlinear terms are non-dominant, then what we can do, we can say that delta V is equal to delta I R plus delta I F dash I. Correct? So this becomes delta I R plus dash I. So what type of equation is this? Is linear, nonlinear? Perfectly linear equation. And we are good in solving linear equations. So I mean, basically the same example, now we are on the river, right? So we can basically solve everything. So what type of, so now this, if I have to draw a circuit, if I have to sketch a circuit for this, right? If I have to sketch a circuit for this equation where voltage is delta V and a current is delta I, right? The new voltage is delta V, not V1, V2, V1, V2, I1, I2. The increment is the input, right? What type of circuit will it look like? And help me build that circuit. So I have, let's say, a voltage source now. Let's say I have a voltage source of value delta V. So how should I complete the circuit? A resistance R, and then another resistance of value F dash I1. Right? So this is that critical step that I am talking about, right? So given that you have, so by the way, is this F dash I1 known to a designer? Yes, because I know the current voltage characteristics a priori. Correct? So I know the current voltage characteristics of a nonlinear element that I'm going to use. So it might be, in case of a diode, it was something like this. In case of another circuit, it might be something like this. It can be something like this. I don't know. But I know that, I mean, wherever we are, so the example that I gave initially was I used the circuit design tool or any nonlinear network analysis or nonlinear numerical analysis to figure out where I am initially, right? Maybe I am somewhere here. So I know, or maybe I'm somewhere here. So I know what the slope is. But now in a nonlinear circuit, your slope is dependent upon where you are, right? So that where you are part cannot be neglected. Where you are is not present here explicitly. Correct? V1, I1 is not present here explicitly. But if I change V1 and I1, will any part of this network change? This extra network that or the latest network that we came up with? What is going to change? F dash I1, great, right? So the slope is dependent on the original point. So the original point, information of the original point is embedded. It has snuck in, but it's not explicit. Okay. So this essentially is this type of analysis, which is essentially valid when we are doing incremental change, or the change is small with respect to something, is called small signal analysis. Right? So we'll learn more about this in the next class.